4.7, everything is dependent on the sun. Atmospheric processes, things like rain patterns, things like wind, things like ocean currents are directly affected by the energy we get from the sun. It's the drive, like wind power we're looking at, that's from the sun. Power from the ocean, harnessing the wave action, that's from the sun. Tidal forces, that's actually from the moon. Energy, gravitational force from the moon pulling it, but that's something else. Input from energy from the sun, and just us humans getting energy from the sun through photosynthesis. And of course, when we talk about the input, we'll have to get to the seasons. So the sun has to get to the Earth's surface. So in order to get to the surface, it's got to pass through the atmosphere. And there's molecules in the atmosphere, air molecules from the nitrogen, from the oxygen. Molecules. Primarily nitrogen, oxygen, water vapor, a little bit of CO2, but you're looking at mostly nitrogen, oxygen, water vapor. And how it gets to the Earth's surface depends on, or how much of it gets to the Earth's surface depends on the location that you're at on Earth and the seasons. So let's get into the topics. This first one we need to be understanding is this word insolation, which is the amount of solar energy that's coming to strike the surface, and it's wholly or greatly dependent on this, the season and the latitude. So here we can kind of make out Los Angeles right about here, and the equator be going right about here. But in this orientation, if the sunlight is coming at this angle, we see this sort of a pattern, a little oblong circle. Here, it's a much more of a perfect circle. In that perfect circle, you're getting a concentrated rate. So it's going to be more energy, more watts are going to be hitting the surface. Plants are going to be able to grow better. It's going to dry out more. Water's going to evaporate at a higher rate. So we'll see, I think I'm blocking it here. The solar radiation is concentrated over a smaller area. And at the top one, we see that radiation. It's the same amount of solar radiation. So the same amount. But here it's spread over a much bigger area, so you don't feel it as much. It's not going to get as hot as where it's concentrated. A larger area. And here's I like this graphic showing, the angle of the sun. You notice this, and we'll take a look at it, measuring the angle of the sun right now, fairly high in the sky at noon. At the end of December, we'll see it's going to take a much lower angle. Like you see in this right here, it's much lower in the sky here during the summer. It's going to be higher. So here is representing the sun in the summer, and down on B is the sun in the winter. There's going to be less energy there because energy is going to be taken out as it goes through that atmosphere. Here it's not traveling through as much atmosphere. So here less atmosphere, less molecules to absorb the rays, to block them. Over here, less atmosphere. Over here, more atmosphere in the winter. And if I let me try to draw this right here. So that's the Earth. This is the atmosphere. This is the sun. So here, straight shot, you got this much atmosphere. But here, you're gonna have a little bit more atmosphere to go. Like the distance between this line and this line is greater than the distance between this line and this line. Here and here versus here and here. Ah, yeah, you can see it's greater. So that greater distance is going to be it's going to be absorbing more of that solar energy, so less hits the ground. Oh, so here, let's mark this up. This is the winter time angle. Not sure. Ours might be around 34 degrees. Not sure. We'll have to check that out. And then here's the summer. Oops, let's say summer. Almost straight up 90 degrees. Not quite, because not quite the equator. Ours might be about the same. So I just looked it up real quick. I was right. I thought so. Our angle in the summertime Long Beach is 79.6 degrees, which is very close to 80. And our winter winter angle is 32.8, which is pretty close to 34 degrees. So this diagram is pretty similar to what we see in Long Beach. All right, next topic. The angle is affected or affects the amount of solar radiation because the shape of the Earth, which is a sphere, and this is a great diagram showing you, classic diagram showing you the orientation of the Earth as it goes around the sun. Remember, the Earth is going around the sun on this tilt. It's 23.5 degree tilt. Tilted on the axis. So this is the sun. Right here you can see we're tilted away 24 December. That's the winter solstice. So I really want you to, write these diagrams down, especially this one. This should be singed in your mind. And right now it's winter in the northern hemisphere, and it's summer in the southern hemisphere. So winter in the northern, summer in the southern hemisphere. I'll say hem. And over here you can see we're in the northern hemisphere, we're tilted towards the sun. So this is going to be the summer in the northern hemisphere and winter in the southern hemisphere. They're tilted away. And the thing in between the two solstices, you should remember this word equinox. It's equal. You don't have an angle, because that angle is right next to or perpendicular to the sun. So you're kind of going like this, like this. This is kind of where that dead 90 degree angle. The graph is showing the amount of insolation based on latitude, and here's the southern hemisphere, and we are positive 33 degrees. So if we were negative 33 degrees, which would be about right here, this is about would be our values in the southern hemisphere. This higher value is going to be December 21st, and this would be the summertime in the southern hemisphere. And this would be our winter. Okay. As we move to the latitude what we are at, which is about right here, we see this line, June 21st, this is our summer solstice. And this line down below is our winter solstice. So when we have these lines showing lots of daily insolation, that's showing you it's summer. Remember, it's opposite for both hemispheres. It gets really confusing. And you can see from this graph, like at the equator, you always have, an even amount of sunlight throughout the year. It doesn't change very much. But the further you get away, the bigger difference there is. Now for us, it's this. You get higher or higher or lower latitudes, you see a much bigger shift. So for us, plants can grow all year long, but it's not like that everywhere. Here's a nice graph, shows you average insolation around the world that hits the ground. Now some of these areas, remember, in order to get to the ground, you need the cloud covered needs to be, clouds reflect sunlight, so clouds can block the light from reaching the Earth's surface. So right along the equator, you don't always see the highest insolation. You tend to see it about 30 degrees up. Like here, these deserts north and south of the equator. And that's because these areas tend to be drier because of air currents. Water is heated up at the equator. It forms clouds. Clouds travel to the north and south, lose their moisture, dissipate. Cool air then sinks, and that cool air doesn't hold much moisture, and it's pretty clear, letting the sunlight shine through. So we get those desert zones, above and below the equator for that, and that allows for more insolation. They tend to be a good place to put wind farms. We talked about the axis of rotation. Remember, it's all about that angle. Remember, some of these diagrams don't show this axis very well, but I chose some that did, just to reinforce that. And just remember those dates for the different solstices.